manufacturing industry in Australia has seen steady declines over the past few decades, as cheap overseas labour has been a preferable way of reducing costs. Evolve Group is a product commercialisation and manufacturing group that has eyes set on reversing this trend by reshoring their manufacturing to Australia. To maintain a competitive hold in the market and reduce operational costs, Evolve extensively utilise automated processes and industrial robots in their manufacturing plant. A recent increase in production due to Evolve gaining new manufacturing contracts has provided motivation to improve efficiency and optimise manufacturing processes.
Evolve Group has approached KM Consulting to design a universal robotic gripping head for integration with their KUKA KR6 robots currently utilised in the injection moulding process. This gripper must be able to pick up and manipulate injection moulded plastic components of different sizes and geometries.
Currently, for each different product that is being manufactured, a custom-fitting robot gripper must be designed, manufactured and installed. The KUKA robot arm must also be programmed to work with the new gripping head design. This entire process generally takes about a week, which significantly adds to the operational costs and reduces efficiency of the manufacturing plant.
Through the development of a universal gripper, our aim is to increase company productivity by eliminating the need to manufacture and install custom gripping mechanisms for each product.
To realistically complete this goal, the project has been split into two phases. The first phase will focus on implementing a universal gripping head that functions for an existing line of products. Evolve has requested that our design first and foremost works successfully with their line of automotive battery lids, covering approximately 20 different designs. The second phase will be committed to expanding these capabilities into a fully automated system that is capable of gripping and manipulating any geometry with the current and future product range. This design will become the single universal gripping head for any requirements. Phase 1 of the design solution must successfully perform the functions that are required to manufacture automotive battery lids. The robotic gripping head first accepts two pairs of the conductive terminal leads from a vibrating rotary feeder. The finished battery tops from the previous cycle are removed from the injection moulding machine. The terminal leads for the next set of battery tops are then inserted into the die. The finished battery tops are checked before being placed onto a conveyor belt for human inspection and packaging.
For phase 1 of the project, my main focus will be to design the gripping subassembly used to pick up and manipulate the automotive battery lids. The design process will explore different techniques for gripping, including existing gripper technologies and also innovative gripping methods. I will be working closely with the team to ensure that the gripping subassembly integrates seamlessly with the surrounding structure.
My focus in the project will be to design the structure that houses the gripping mechanisms and auxiliary components, connecting them to the KUKA robot arm. The current robot gripping head utilises a single piece of rigid aluminium structure that is custom designed to only work with the geometry of the individual battery lid and cannot be used to grip any other products. Phase 1 of our design solution focuses on a structure with inherent degrees of freedom, allowing the gripping points to move depending on the geometry of the battery lid.
As a systems integrator, I'll be focusing on the system as a whole, ensuring cohesion of the sub-assemblies within the design and the integration of our design into the existing process. Each sub-assembly within the design is linked and dependent on one another through a wide range of mechanical, electrical and pneumatic connections. To successfully operate the whole system, these connections must be programmable such that the motion, position and actuation of sub-components can be controlled.
To extend the capabilities of the robotic gripping head, phase 2 of our design solution will be to integrate other grippers into the single robotic head. Different gripper types will allow for the robot to pick up and manipulate a more diverse range of parts and geometry, making it adaptable for use with any injection molded part. I will be exploring and designing these gripping mechanisms, ensuring that they provide a comprehensive range of gripping options.
To ensure a fully autonomous system, the robot must select from a range of interchangeable grippers. The specific gripper to be utilised for the role will be retrieved from an array containing the gripping heads. For the system to be successful, the robot must have a method for identifying what gripping head is to be used per product distinguish the location of these heads within the array, and determine the tasks required to be conducted for each product. Integration of the system will require a major overhaul behind the programming of the current system.
Phase 2 of the structural design will focus on automated socket points that will allow for the automatic gripper change. The two key problems that have been identified are the design of an automated locking system for the interchangeable grippers, and the design of an interface capable of transmitting the work required for actuation.
The preliminary design stage has provided a comprehensive range of ideas and possible solution scenarios through the assessment of current design practices and research of prior art. We have evaluated these scenarios by reviewing the wishes and requirements of the client, leading to a two-stage delivery solution. The first phase focusing on the design of a robotic gripper that can successfully operate for a range of 20 automotive battery lids. And the second phase will extend on these capabilities as an all-round universal gripping head. The conceptual design and evaluation stage will use 3D design and modelling software to refine and assess the design to prepare for an initial prototype development. It is expected that this stage will be completed by the end of July.
Prototype assessment and ongoing refinement will subsequently commence until the manufacture and delivery of the final Phase 1 design is completed, which is expected in late August. This allows for the basic operating structures and requirements to be fully implemented before the alteration and delivery of the final Phase 2 solution, which will be delivered in October.